So impulse turbine, so I said like impulse turbine, reaction turbine can be used for your steam turbine system or a marine machinery. So what is impulse turbine? Impulse turbine converts kinetic energy of fluid into mechanical energy. The rotation is a result of change of momentum. So when fluid is flowing through this, you can see I have drawn already this impulse turbine. Actually, this is one turbine blade, this is another turbine blade, this is my guide vane, this is my guide vane, this is my guide vane, this is my guide vane. And here you can see the same turbine in 3-dimensional picture we have drawn here like this. Okay, these are impulse turbine blades, and complete blade is looking like this, you can see, right. So complete blade is looking like this. So there will be several, maybe 35, 36 blades, okay, all around this hub. This is hub, okay, this is hub, okay. On hub, the impulse turbine blades are fixed. The stator blade, these are stator blade, the stator blade. So stator blade, actually this one also, and this is rotor blade, this is rotor, okay. Rotor blade will be on the hub, and when hub is rotating, the yellow part is rotating, the red part also will be rotating. But stator, this will be fixed on your casing, okay, because casing if we show, then 3-dimensional you cannot see here, so that's why casing is not shown here. So stator will be fixed on casing, and stator is not rotating. Okay, rotor is only rotating. And what is happening? So fluid, you can see this, I am drawing with pen. Fluid will be going like this, it will give energy to this blade, then again it will be exiting, okay. So rotor blade will be getting energy, stator blade will be guiding the fluid, okay. And if I have multiple rotor blade rows, so one rotor blade rows, another row, in between there will be guide vane. So guide vane will be changing angle to give proper angle to rotor blade. So guide vane purpose not to harness energy, rather to give angle to rotor blade. Rotor blade will be only harnessing energy, okay. And another turbine here I have shown, because in my laboratory we have worked on this both turbine, impulse turbine and reaction turbine. The Wells turbine actually symmetric blade turbine. The symmetric blades are there. You can see this symmetric airfoil shape is there. These are the blades. These are the whole blade is here and symmetric shape is here. Okay, so normally 8 blade turbine we design. In symmetric Wells turbine blade, this is actually a reaction turbine. So in reaction turbine, fluid will be passing through the blade passage. These are passage, okay. Through this passage, blade fluid will be flowing, and it will be rotating in this direction, okay. Rotation like this. This system rotation direction is this rotation direction, okay. And in between two blade, they call passage, okay. So two blade space, this space is called passage. Okay. In reaction turbine, both kinetic energy and pressure energy of flowing water or fluid, it will be converted to mechanical energy. So Wells turbine will be harvesting energy, and it will be taking energy, kinetic energy plus pressure energy from fluid. Blade rotation due to the pressure difference across the blades. But impulse turbine, we basically harness kinetic energy. So more kinetic energy, more energy will harness from impulse turbine. Here some picture from a laboratory. Actually we designed this 3D impulse turbine blade. This is impulse turbine actually. You can see this impulse turbine blade is like this, crescent shaped, okay. So these are blade from my laboratory, okay. So I have around 36 blades we have, and this is a guide vane. So guide vane, you can see axial flow will be coming like this, and it will be turned, and after turning, what it will do, it will be entering to this blade actually. So one guide vane, one turbine. So we made a guide vane in using metal, and the rotor blade using softer material, 3D printing we use, and guide vane will be guiding my flow, and it will be giving to rotor, and rotor, after rotor also there will be guide vane rows. So I am not showing everything here. In below picture I can see one biplane Wells turbine. There also we designed this one, we tested in our laboratory at IIT Madras. So there also, this is a new type of turbine. So this is called biplane Wells turbine. This is normal Wells turbine I have shown before, okay. So these are actually wave energy harvesting turbine, and this is called tidal turbine. Okay. Now impulse turbine and Wells turbine, this is taken from energy cyclopedia of life support system, ULSS. Here impulse turbine are like crescent shaped blades are there, you can see here, and reaction turbine blades are like this, airfoil shaped, you see right side left side both. And impulse turbine, pressure going down gradually. In reaction turbine also pressure is going down gradually, you can see bottom pictures. But absolute velocity, what is happening, impulse turbine inside turbine rows, actually velocity going down. You are giving very high velocity, and fluid is transferring energy to blade. After that your fluid velocity will be reducing, okay, but your pressure is constant. But in reaction turbine, what is happening? Let us see inside blade what is happening. In reaction turbine also velocity is going down, but pressure also going down, because reaction turbine is harnessing energy from both, so both are going down. But impulse turbine, only velocity going down. Okay. So application of equation motion, conservation of mass, momentum. Okay. Now whenever you are solving any fluid dynamic problem, so you have to remember mass conservation, momentum conservation, and energy conservation equations. So if there is heat transfer happening, normally energy conservation equation will be solved. If heat transfer is not there, so normally we will be solving momentum and mass conservation equation. Okay. So this is mass conservation equation, mass you cannot destroy. So rho AV, so if I have turbine inlet 1, you see right side picture, turbine inlet at 1, exit at 3, in between pressure section is 2. So in that case I can write like rho 1 A1 V1 equals to rho 2 A2 V2. Okay. So whenever fluid is flowing through turbine, mass will not get destroyed. So mass, inlet mass and outlet mass you have to check, same mass you have to get at outlet also. If you are not getting, then you maybe you have done some calculation mistake. And your let us say I have one turbine, you can see this turbine, this shaft is here but hub is here. Okay. So I have one turbine here, turbine hole is here and turbine hub is here, my blade is here. Okay. Yes, I am drawing 4 blades on turbine, and this is my hub. So blades are placed on hub. Okay, this is my hub and blade is placed on hub. So this is hub and this is center of axis, or axis only, and this is a blade. Okay, this is blade height. Okay, so this right side picture you can see my axis of rotation, or center of axis, instead of center of axis I can write axis of rotation. Axis of rotation. Okay. So from axis of rotation, hub radius is RH and tip radius, blade maximum distance from axis is called tip radius. So R tip, and whenever fluid is flowing, it is not flowing through hub. Okay. So we have to calculate mean radius of the blade. So RM, this is RM, mean radius of the blade. Okay. So A, so at inlet, what is the area of flow? Area of flow equals pi R T square minus R hub square. You see, hub radius and tip radius, in between that space, that will be used for your fluid flow. So that's why the fluid flow area is RT square minus RH square. So mean blade radius RM, mean blade radius is RT plus RH by 2. Now 2RM equals RT plus RH. Okay. Now blade height, B equals RT minus RH. Okay. Therefore A equals pi RT, you can see here, RT plus RH, RT minus RH equals pi. RT plus RH means 2 Rm, Rm into RT minus B. Okay, so 2 pi RmB. Now, whenever you have turbine, I said turbine expands steam. Okay, so turbine, let's say this is my axis of rotation, this is my hub, and my stator is here. Okay, then my rotor will be on hub. Again stator will be there, rotor will be on hub. Okay, and normally this is expanding. So okay, so normally this turbine will be expanding. So my hub, rotor is, stator is here, rotor is here, stator is here, rotor is here. So gradually my rotor size will be increasing, or stator size also will be increasing. So a turbine operates at 8.8:1 pressure ratio, the mass flow rate 77 kg, exhaust temperature 43, inlet temperature given, mean radius also given, means center axis to mean radius 0.4. The turbine design constant velocity u equals 200 meter per second. So B you have to find at inlet, at outlet. So here B, and at left side and right side you have to find. Okay, so to solve this problem, we have to calculate P by rho equals RT. R equals 287. Maybe we have to give R value also. J per kg, kgk. So 287. So P1 equals 8.8 bar equals 8.8 into 10 power 5 Pascal. P2 equals 1 bar equals 1 into 10 power 5 Pascal. T1 equals 1000 plus 273 equals 1273 K. T2 equals 473 degree centigrade equals 730 K. So rho 1 equals P1 by RT1 equals 8.8 into 10 power 5, 287 into 1273, 2.41 kg per meter cube. Rho 2 equals P2 RT2 1 into 10 power 5, 287 into 1710, 0.49 kg per meter cube. So m dot equals rho A V equals rho 2 pi R m B V, implies B equals m dot rho 2 pi R m V. Therefore B1 equals 77 2 pi into 0.4 into 200 into 2.41 equals 0.06. B2 equals 77 2 pi 0.4 200 into 0.49. So it is coming 0.31. So this is the answer. Thank you very much for listening to the lecture. Next day we will start next topic on steam table and enthalpy calculation. Thank you very much.